in some rare instances, stretching it or shearing it in any of the dimensions. So the trivial use for these transformations is what Hume was just describing, making sure that an image, even though it's stored physically on your hard disk as in radiological format, will always be seen by you as in neurological orientation. But often these transformation matrices, or little 4x4 matrices, are used to represent the relationship between different images in your volume, specifically between two images that are maybe taken from the same subject, so they do have a sort of physical correspondence of shape, but may not be in the same place in the image. So this is another way that two images can be in the same space, even if the coordinates in the volume don't actually align the two images properly. A transformation that's stored separately can show you how to transform those coordinates in a way that aligns the two volumes. So, as a practical matter, what this means is that what you see in the files isn't always what's really in there, or vice versa, depending on which way you have the flag set in your image viewer. And furthermore, that sometimes what you have, you'll have data stored alongside the image file that's actually very important in representing spatial transformations that may have been calculated for that image. Typically, if you're doing an fMRI study, this is required for things like realignment of volumes and for co-registration of functional and structural data. But it's also potentially useful in lesion analysis for co-registering different modalities that may have acquired. So that's all I'm going to talk about for the moment, and I'm going to turn it over to Hun, who has slides that we really hope.
Before you turn it over to me, the transformation, you said it's stored in the Nifty file. It's quite confusing. Where in the file it is stored, like in the header, or how can we find out, or can we manipulate it somehow?
So yeah, so in Nifty files, there is a space in the header for affine transformations. And there's actually 3 different ways to store orientation in Nifty files, and every software package supports a different subset of those 3. So although it was supposed to make things easier, I think in many ways it's made things more complicated. But what's worse is that the Nifty file header only has a way for storing 1 image's worth of orientation information. So if you have a 4D file that has 100 different 3D images, it can't store all the transformations in the header that way. So you'll typically then still have to create an external file with the transformation information. I frequently, as part of what I'm, when I'm trying to make sure I do the right thing with images and know what's there, like to zero out an orientation information, basically to set it to the default, so that the orientation and the actual physical arrangement of data in the file are congruent. So here's the CH2 volume. If I do VBI-F CH2, you can actually see this little transformation matrix, which right here is just set so that it's nothing's rotated, nothing's sheared. It's just sort of representing the origin of the image, which is represented by these 3 numbers in the right here. It's just saying that's where the corner is relative to the origin. But you can also, there's a VBIM command. Let me see if I can find it. Set space. Okay. So what I've done is run set space without any arguments, and this zeroes it out. So now I can do now I can look at this, and you can see on the right hand side there, it's actually zeroed out the origin component of that Nifty file.
So that matrix is actually the same thing as when you get when you type print header in ANT's tool.
Yeah, but yeah, this is the whole Nifty header. So yeah, these are the transformation these are the transformation matrices. And these two rows are the other bits of header information that are sometimes used, sometimes not. Yeah, so.
And just one other thing about origin. There are physical origin and also voxel origin, and is physical origin specific to Nifty file format?
When you say physical origin?
Yeah.
What is that? I don't know what that means.
So there, it looks like there are two types of origin. As far as I know, there are physical origin, which doesn't change even if you resample it to different resolution. So I've seen that physical origin specified in Nifty file before, so it was very confusing to me. So.
Well, yeah, I don't know what that term means. There are two places to store an origin. One is as part of transformation matrix, and the other is in these Q offset fields, but they're not really supposed to be used together. It's possible that is it possible that physical origin is something that was calculated by the software you're using from the other orientation information?
I don't know.
What programs says?
Ants.
Ants.
So probably Olu might have some.
I'm not quite. The only thing I can think of is it possibly that it's an origin that's set from the scanner.
No.
Yeah. Well, if it's calculated from Nifty files, it's getting them somewhere from this header. I don't imagine I imagine it's calculated from the same orientation information.
Okay.
Probably if you sat down with a calculator, you could figure it out. But I don't have Ants on here right now, so.
Right.
Okay, no stalling. You have to get some time. You're not going to do 29 slides, are you?
No. Yes, I will.
Really? Well, you're off the hook.
Yeah, so I'm gonna just blast through the 29 slides that I have. Just interrupt me anytime you feel you are uncomfortable. I should. Spatial registration was actually very confusing and frustrating field for me. But I had to deal with it because I studied injured brain, and but the most difficult part was that I know nothing about math, and a lot about spatial registration is math. So I think the reason why I say is that you can you don't have to be threatened by the contents of this, and we can share our frustration together. I should acknowledge my collaborators, Brian Evans, Jim G, John White, and a special acknowledgement to Matthew Brett and John Ashburner because I stole several slides from them. So this is about putting everybody's brain into a standard space, something like space and template. This template, and these are different. This is typical situation in fMRI, and you work this different subjects anatomical image, and then you get work. The individual work and apply that to functional images, and then put everyone's functional image into template space, and then you get this statistical parametric map that's the kind of gist of how spatial registration normalization is used in fMRI. So we have this challenge. The brains we are dealing with are characterized by largely two types of lesion characteristics. The first is diffuse lesion on the left panel, and enlarged ventricle and sulcal space, things like that. And on the right panel, focal lesion. So spatial normalization faces this challenge, and this is the issue we have to deal with. One primitive way of dealing with this issue is something called affine transformation or linear transformation, and it determines the optimum 12-parameter affine transformation to match the size and position of the images. So this is rotation, this is translation. So you move, red square to the position of the green square, and this is zooming x or in x direction or y direction. This is shearing, and it twists the image, but it preserves this parallel relationship between lines. So this bottom panel shows how this source image is translated, rotated, and zoomed and shared.
I have a quick question.
Yes, please.
So I know Dan a second ago was talking about affine transformation using Voxpo. I know your method is to use ants. So essentially just using two different programs to do the same transformation here. Is this fine? Because I know you can use ants to do the entire registration process, but is it fine to go with either method here?
Yeah, so I see no problem you're doing affine transformation in other software, SPM or Fossil, Flirt, and then taking that image to ants and do the nonlinear working there. Olu will talk about the specifics about how to do how to implement the whole thing, the whole registration process. I'll talk about more conceptual issues in registration. So
there is one good reason why you want to do everything in one piece of software, which is that every time a lot of the software will do the affine and then the nonlinear transformation as sort of separate pieces. And what you can do if you're doing it in the same software package is actually calculate both those transformations, but then apply them together. So that you don't result in this every time you resample the image, every time you sort of actually apply the transformation, you degrade the image a little bit. So if you can calculate both transformations, combine them together, and then apply them all at once, you only degrade the image once.
Right. So sticking with within one image, one software package is good. Dan just mentioned a minute ago about this voxel counting issue starting from 0 and 1. It's trivial when that 1 is 1 millimeter, but if your voxel size is like 4 millimeter, then it's pretty sizable shift. So this is typical brain, TBI brain with diffuse injury, and this is very big fat brain. This is actually my brain.